In today's video, we're going to start on our chapter that looks at probability. So in this section, we look at experiments, outcomes, sample spaces, and events. The first thing I want to do is to actually define each of those terms so that as we go through this chapter, we know exactly what all of these mean, as they will come up time and time again. So an experiment is just an activity that has an observable result. What does that mean? Well, think about things, the two obvious ones that we look at time and time again throughout this chapter are rolling a die and tossing a coin. Both of those are experiments, okay? You conduct the activity of rolling a die or tossing a coin and you have observable results, either the numbers 1 through 6 or heads or tails. Okay? Each possible result that you get from this is called an outcome of an experiment. So the outcome when we roll a die could be the numbers 1, 2, 3, 4, 5 or 6. They're all outcomes. They're all results that we can get. For tossing a coin, we could have heads or we could have tails. That's an outcome. Okay, so each of those possible observable results is called an outcome. And then the set of all possible outcomes is called the sample space. So the sample space for rolling a die would be the set of numbers 1 through 6. The sample space of outcomes when we toss a coin is going to be heads or tails. So the sample space is just all possible outcomes. And then an event is just going to be a set of these outcomes. It's a subset of the sample space. So an event for when we roll a die could be the event of rolling an even number. Okay, that's the set of outcomes 2, 4, and 6, which is just a subset of our sample space. Okay, so an event is a set of outcomes, or you can also phrase it as a subset of the sample space. Okay, so that's what each of these 4 terms means. So whenever we go through this particular chapter, you will know whenever we refer to each one of these 4 things exactly what we mean. I'm going to go through 3 examples that are going to come up time and time again, and they both refer to rolling a die or tossing a coin. And they come up all the time whenever we refer to probability problems. Okay. So our first example is going to be rolling a die. Okay, and I'm going to look at each of those 4 terms and see what they mean in terms of rolling a die. Okay. So first thing is, what is the experiment? Well, the experiment is the actual activity of rolling the die. So the experiment here is just rolling the die. Okay. The next thing is the set of outcomes. So the outcomes are just the numbers 1, 2, 3, 4, 5, and 6. That's a set of all possible results that we can get from rolling a die. The sample space is the set of all outcomes. It's going to be the set 1, 2, 3, 4, 5, and 6. And then an event, okay? An event here, there are many that you can have, but I'm going to pick the event of rolling an even number. That is the set of outcomes 2, 4, and 6, and it is a subset of that sample space. Okay, so for this particular experiment of rolling a die, that is how we are defining each of those 4 things. And like I said, with event, you can have many, many different events. You could have had rolling an odd number. You could have had rolling a number that's less than 3. Okay, you can have many different events, but I just picked one specific one in this case. I'm going to expand this for my next example and look at rolling a pair of dice. Okay. So now, instead of just rolling 1 die, I'm rolling 2. Okay. And we're going to look at what possibilities that we have. So again, the experiment here is just rolling the 2 dice. Okay. The outcomes. Okay. Each outcome now is going to be a pair of numbers, because you're going to get the number from the first die and then the number from the second. Okay. So each of your outcomes is now going to look like a pair of numbers like this. We'll call them A, B, where A will be the number that you get from the first die, B will be the number that you got from the second die. Okay, and each of A and B are between 1 and 6. So that leads us to our sample space. What is our sample space? Okay. There are 36 different outcomes that you can have here. Okay, I'm not going to do all of them, but I'll start off what our sample space would be. So you can have 1 on each die. You can have 1 on the first die, 2 on the second. You can have 1 on the first, 3 on the second, and you keep going. And then once you've gone through all of those possibilities, then you look at the possibilities of rolling a 2 on the first die, 1 on the second, 2 and 2, and you're going to go through all possibilities of A and B being 1 through 6 until you reach where they're both 6. So there's 36 different possibilities of outcomes here. There's 36 outcomes, so our sample space has 36 different pairs in it. Okay. Again, there are many events here that we can have. For rolling 1 die, I just looked at the possibility here where we had even numbers. Okay, so 2, 4, and 6. But here I'm rolling 2 dice at the same time. Okay. So what I'm actually going to do for my event here, again, there's many of them, but I'm going to have the event that the sum of the 2 numbers is 4. Okay. So out of my 36 different elements in my sample space, which ones give me a sum of 4 when you add those 2 numbers together? So I can have 1 and 3, where I got 1 on my first die, 3 on my second. I can have 2 and 2. And I can have 3 on my first and 1 on my second. That's all possibilities, Okay, so this particular event only has 3 different outcomes in it, but again, it's still a subset of my sample space. The next example I'm going to look at is tossing a coin, and I'm going to actually do it kind of like I did with this second example, but this time I'm going to be tossing a coin 3 times, so I'm doing this thing multiple times. Okay. We know what our experiment is. It's just tossing this coin 3 different times. That's what our experiment is, and we're going to look at what the outcomes are. So the outcomes here, okay, it's going to be 3 different things, because again, we're tossing the coin 3 times, where each time we can have heads or tails, heads or tails, heads or tails. So our outcomes are going to have 3 different entries in them, heads or tails, in a row of 3. And then we've got to look at all different combinations of heads and tails where we've done this 3 times. Okay, so that leads us to our sample space. Okay, what does our sample space look like? Well, I can have heads, heads and heads. So where I've tossed this coin 3 times, every single time I've got heads. I could have heads, heads, tails. I could have heads, tails, heads. I could have tails, heads, heads. So that's all 3 possibilities where I've had 2 heads. And then I could have heads, tails, 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 heads, tails, 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 heads. So that's all the possibilities where I've got 1 head. And then I can have tails, 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 where I've got no heads. Okay, and that's all 8 possibilities. So that is the set of outcomes that form my sample space. For an event, again, many different options. I'm going to look at the event here that exactly 2 heads occur. Okay, what does this look like? So I need to look at the outcomes in my sample space where I have exactly 2 heads. So that was heads, heads, tails, heads, tails, heads, and tails, heads, heads. Okay. So now I want to tie in this probability stuff that we've been looking at with Venn diagrams, unions, intersections, things like that. So let's say that I am doing this experiment of rolling a die, and I have the event, we'll call it E, of rolling a number 3 or greater. So E is going to have this set of outcomes. Okay, and then F is going to be the event of rolling an even number. So F has these outcomes. Okay. The union of 2 events, okay, be E union F, is going to occur when either E or F or both occur. Okay, so let's draw this as a Venn diagram. So let's say inside this circle we have all of our outcomes that are in the event E, and in this circle we have all the outcomes that are in our event F, and then this will be our sample space. We'll call it S. So S is just going to be, if we're doing the experiment of rolling a die, S is going to contain all the numbers 1 through 6. E just contains the numbers 3, 4, 5 and 6, so it's rolling at least a 3, and F is going to contain all the even numbers. Okay. E union F occurs when E or F or both occur. Okay, so on a Venn diagram, that would be everything inside the circle E, everything inside the circle F, including that part where E and F overlap, so both could occur. Okay. In our case here, E union F, let's look at what would actually be in that particular event, E union F. So that would be 2, 3, 4 occurs in both, 5 and 6 occurs in both. So 2, 3 and 5 land in one of them, 4 and 6 land in both. Okay. Then we can have the intersection of two events. So that would be E intersect F. And that occurs, E intersect F occurs when both E and F occur. So you have to have both of them happening at the same time. Okay. So going back to our example here, that would just be this middle section where E and F overlap. So if we draw this as a Venn diagram again, this is our event E, this is our event F. This outside box, everything inside it is going to be in our sample space. So for our example here, that would be for rolling a die, all numbers 1 through 6. Okay. E intersect F is just when both occur. So it's that overlapping section on a Venn diagram. What numbers in our example would actually be in E intersect F? It's the numbers that are in both sets. So 4 occurs in both and 6 occurs in both. So for our example, E intersect F is 4 and 6. Then we have the complement of an event. We'll look at the complement of the event E, okay? Like before, we denote that as E prime with just a small apostrophe above it. And that occurs when E does not occur. So it's all of the, in our case, the numbers that are in our sample space but are not in E. So that particular event, the complement of E, that occurs when E does not occur. What would that look like on a Venn diagram? Well, let's draw our event E. Okay, you could have more circles, like you could put in F here, etc. But basically, just to show you what it would look like here, if that is E, then the complement of E is everything that lands outside of E. So exactly the same as when we were looking at Venn diagrams before. If you have more circles, you could shade those two as long as they weren't in that overlap with E. Okay, so anything that overlaps with E, you don't shade that overlap because E is not in the complement. Okay, the complement of E is everything that lands outside that circle of E. Okay. So going back to our example, the complement of E here, that event, we said that E was rolling a number 3 or greater. So that would mean that the complement of E in our case would be everything in the sample space that does not fall in E, which would be 1 and 2. The last term that I want to look at is the term mutually exclusive. So two events, E and F, are said to be mutually exclusive can also be called disjoint. So if you ever see the term disjoint, that's the same thing here, but most of the time you'll see it as mutually exclusive if the intersection of E and F is just the empty set. You can write it two different ways. You can either write it with two brackets with nothing in them, or with that circle with the line through it. So two events E and F are mutually exclusive if they do not overlap on that Venn diagram. There is nothing in that intersection. So if you draw it as a Venn diagram, it would literally just be a circle E and a circle F with no overlap. Okay. An example of this would be, let's say you had E was the numbers 1, 2, and 3, and F could be the numbers 4 and 6. You could have 4, 5, and 6. That would also work. But the intersection doesn't contain any elements, okay? It's the empty set. So E intersect F in this case is the empty set, okay? So whenever you find that that occurs, then the two events are said to be mutually exclusive.